Hello, welcome to today's lecture on color and power mode. So in previous lectures, we had discussed the Doppler principle as well as the pulse Doppler and continuous wave Doppler modes. We also talked about how to do spectral Doppler. So in this lecture, we'll continue and talk about the color and power Doppler modes that are frequently used in the clinic. Now, what is color flow Doppler imaging? So this one provides a 2D cross-sectional image depicting the velocities and flow direction of moving reflectors and scatterers inside a vascular system. So here you can see that this is an example of a color flow Doppler image, wherein in the bottom you have a spectral Doppler display, and in here you see that B mode, which is overlaid with a color map, and this color map corresponds to color Doppler. What's nice about this mode is that it can be duplexed with B mode. And so you can have the advantage of getting the anatomical details with B mode, as well as getting the physiological flow information with color Doppler. Also, it provides real-time flow visualization, and it can help delineate a wide range of flow conditions, including those of diseases, such as wherein you have stenosis in a vessel or a narrowing of the arteries. You can also use it to assess regurgitation or backflow in the chambers of the heart. In terms of acquiring the data, so this is what the data acquisition schematic look like, wherein you have B-mode lines here coming out of the transducer. The B-mode lines are situated at various lateral locations to look into a region of interest. And within a region of interest, you can also select a region wherein you will calculate the color flow Doppler signal or the blood velocities with the direction. So within this green box here, I'm highlighting what's called the color flow box, which one can indicate in the Doppler display. And here you have your B mode lines as well as what's called the color flow packets, which we'll discuss further in the next few slides. And these are technically windows of the color Doppler signal that you will look into at different depth locations in the region of interest. So looking at what the transmit pulse shapes are and how they're different between B mode and Doppler. So in B mode, you would recall that the pulse is typically 2 or 3 cycles. It might look something like this. And in color and Doppler, you can see that the number of cycles is much more, typically on the orders of 5 to 10 cycles. And the longer the cycle means that the bandwidth of the signal will be narrower. So in this case, the Doppler and color flow pulse signals typically have narrower frequency bandwidth. And this is useful to have good resolution in your color flow Doppler images. When we talk about processing of the echo signals for Doppler, so here's just a schematic of your echoes coming into the transducer. So for instance, here you have an echo signal from a particular reflector, and then a second echo signal that is shifted in time, as you can see here. So in this case, the signals are phase shifted. And when you're computing the Doppler echo signal values, what's also important is the phase of the incoming echoes, because that also relates to the depth or the distance at which the reflector is from the transducer. What's also important is the echo amplitude, and that will be useful for assessing the intensity of the blood flow display in color flow Doppler. And the way color flow Doppler works is that first you transmit a pulse, and then you would collect echoes from different pulse packets, and each pulse packet is one pulse echo sequence. And within this pulse packet, the echoes will be saved into a register, which retains information for a different window at a particular depth. So you can imagine that a transmit signal is being sent to a particular lateral location, and it's going through a function of depth, and the echoes are being received at each individual depths. And this pulse echo sequence is happening in order to be able to assess the flow or the velocity of the scatterers inside that region of interest. And the more pulse packets there are, that means there are more accurate blood velocity estimation. However, to get an entire color flow image, it will take some time to form the image based on these pulse echo sequences. Therefore, if you have more pulse packets, then it might result in slower imaging frame rates. So there's a trade-off with color Doppler here and the imaging frame rates. Now this is just looking into the color flow imaging system. What we have here is our transducer. Now it's emitting the transmit ultrasound signals. It's going to interact with the reflector. The reflector will then send, there will be an echo signal that will be reflected back from that reflector. And then that echo signal will be received by that transducer, and then Doppler processing will happen in terms of looking into the echo from the first pulse and then the echo from the second pulse. And what's going to happen here is that the signals will then go into an autocorrelator. And what this is, it's a phase shift autocorrelator, which estimates the changes in the phase between the two between echo signals. And this is useful for computing the mean Doppler frequency and the velocity at each depth within that axial location. So then the signals get saved into a temporary storage unit, and afterwards, within that temporary storage unit, can map the velocities as well as the variance estimates for detecting the presence of turbulence in blood flow. So the velocity, of course, is important, but the variance estimate is equally important because that will also give you an indication whether there are how much differences or variations there are within a region of interest. So if you look at this image on the right here, we have a blood vessel, but afterwards it reaches a location in the tissue where you can find multiple colors, large variations in the velocity estimate here. And what one can do is you can estimate the variance of these blood velocities at this location, and that can give you an indication of how much turbulence there is here. And that's useful for assessing certain diseases within that region. And afterwards, after these estimates, then it saves into the color image memory, which will then be used to map your color Doppler display. So now let's talk about the properties of color displays. There are certain image properties that are based on the psychophysical perception of color. One of those properties is called hue, and that's typically related to the wavelength of the visible light. So in a color Doppler image, the map is typically based on a red hue, which means that the reflector is flowing towards the transducer. So if you can see the color map here, this is a color Doppler map overlaid onto a B-mode image. Here, red to bright red means that the flow is moving towards the transducer, and the brighter intensity of that red means that the reflector is moving faster. And in contrast, if the scatterer or reflector is moving away from the transducer, then there will be a blue hue in the color Doppler display. So you can see here the color map. You have from blue to even brighter blue. That corresponds to the reflector moving further away from the transducer, and the brighter the blue means that it's moving faster away from the transducer. So the intensity also matters when I talk about the measure of the brightness of that hue, and that indicates the flow rate. There is one component that's very important in terms of adjusting your Doppler display. Let's talk about the concept of aliasing. So you might have remembered in your signal processing class this concept, wherein if you have a signal here and you sample it at certain intervals, depending on how often you sample it or the sampling rate, you will get a recorded signal. If you sample it enough, then the recorded signal will be similar to the original signal. But if you sample it too low, then the signal will have a lower frequency component. So basically, the sampling rate of the system does matter when you're talking about color Doppler and being able to avoid this aliasing artifact. And there's a limit on pulse repetition frequencies in these pulse and color Doppler systems, which limits the sampling rate. And as you can see here, if there's aliasing, then lower frequency components are developed. And several factors that can cause that is if you have really high velocities in your blood flow and your pulse repetition frequency is not enough to capture those high velocities. Also, if there's an increasing depth in the region of interest, that can cause some range ambiguity. In a previous lecture, we talked about range ambiguity in terms of an imaging artifact. Also, if the operator dials an inappropriate Doppler angle, that can also affect the Doppler frequencies that's being measured, and then consequently the blood velocity. And if you have a large sample volume, let's say you sample a really large vessel, and you have a range of Doppler frequencies ranging from low towards the sides of the vessel and going really high towards the middle. So if you're trying to capture all that range of Doppler frequencies, then it might also be that the frame rates will not be adjusted properly. So one should keep in mind the aliasing phenomenon, and we'll discuss a way that you can do to be able to remove or eliminate this aliasing phenomenon. So this is an example of an aliasing artifact, where here I show a color Doppler image, and below is the spectral Doppler. What you can see in the spectral Doppler display is that you have this wraparound phenomenon. So this is what I'm pointing at is the baseline of the spectral Doppler here. The higher velocities are because of higher Doppler frequencies, and then the lower velocities are because of lower Doppler frequencies here. The bottom part of the spectrum indicates that the flow is moving away from the transducer, and the top part, again, is indicating that the flow is moving towards the transducer. So when the flow is moving away, then you get these negative velocities. When the flow is moving closer to the transducer, then you get positive velocities. If aliasing happens, then you get this wraparound phenomenon right here, where it appears that the high velocity reflectors are actually being read as lower velocities. So these components of the spectrum that are in the low velocities are because of aliasing of the high frequency parts of the signal right here. And then the color Doppler display, what you can actually see is a mixture of blue and red hue and in the intermediate parts as well. So typically a healthy vessel would have either a red or a blue hue depending on the direction of flow. And if you find that there's a region where there's a mixture of red and blue hue, that means there's some turbulence in there, or it's because of some inconsistent PRF or very low PRF due to this aliasing artifact. Now, what is the maximum velocity that you can detect with pulse Doppler? So there's a very simple criterion that one has to follow to avoid aliasing. So you must have remembered the Nyquist sampling theorem, right? Well, in Doppler, if the pulse repetition frequency is at least twice that of the Doppler frequency, then you can avoid aliasing. So let's look at how we can calculate that maximum velocity to avoid this aliasing. So here, V max here is, we'll consider that as our maximum reflector velocity. PRF max is the maximum PRF from a sample volume at a certain depth. Okay, so this is within your smaller windows along the axial depths of your region of interest. So then to avoid aliasing, in this case, let's assume a Doppler angle of 0, meaning that the flow is moving directly towards the transducer. So if the Doppler angle is 0, then cosine of 0 equals 1, and you'll get the maximum velocity when the reflector is moving directly towards the transducer. So the pulse repetition frequency, the maximum, should be at least 2 of the times the Doppler frequency. And if you plug in the Doppler equation into this, now the cosine term is gone, because if you assume a Doppler angle of 0, then cosine is just 1. So there's no cosine term here. So then in terms of rearranging this equation, okay, so we'll isolate Vmax here, and so Vmax will equal the sound speed, the max pulse repetition frequency, and 4 times the transmit frequency, F naught, right here. So that will equal about square of the sound speed divided by 8 times the transmit frequency and the depth of that location. Okay, and the Vmax will vary depending on where you are actually in that beam line, okay, which depth you are in that beam line. Now let's look at an example of how we can use this expression to be able to compute the maximum detectable blood velocity. So we asked the question, what is the maximum detectable blood velocity if the ultrasound operating frequency is 4 megahertz? So this is our transmit frequency. And the vessel of interest is at 5 centimeter depth, 5 centimeter away from the transducer. When we compute, we can you can see here where, okay, if we assume that the speed of sound is 1540 meters per second, utilize this expression here. We plug in for the speed of sound, the 4 megahertz, this we're going into meters per second right here. So that 4 times 10 to the 6 is therefore megahertz, times 5 centimeter depth, or 0.05 meters right here. Plug in these, calculate, you get 1.48 meters per second. Typically, when we talk about blood flow velocities in the body, it's in terms of centimeters per second. So in this case, our maximum velocity is 148 centimeters per second. So if the vessel was deeper than 5 centimeters, then the maximum detectable velocity would decrease, as you can see based on this inverse relationship between the maximum velocity and the depth. So the deeper you are, where your depth window is, then the maximum velocity decreases, and vice versa. So where these can happen in the body is anywhere, like for example, the heart, where if cosine theta or cosine of 0 Doppler angle is 1. If you image in the heart, the blood flow can be in various directions. So depending on your image field of view, these Doppler angle can even go into 0 degrees. Now, how do we eliminate aliasing? So there's one way that's typically used, and it's by increasing your pulse repetition frequency. So what I'm showing here are some examples of, this is a similar image that I had shown earlier. So here, the color Doppler ultrasound was being done at a pulse repetition frequency of 1.5 kilohertz here. And you can see by the spectral Doppler display, there's a wraparound in the spectrum. And this implies aliasing, as well as a mixing of blue and red, right? So this is also an indication of aliasing. And so what you can do is if you increase the PRF to 3 kilohertz right here, that means you will be able to sample faster. Sampling rate is faster. You can get more of that sampling, that higher frequency components. Then you can see that the flow through this vessel is very smooth, just red. And in the Doppler spectrum here, you can see that the y-axis right here shows only positive velocity components. So this is one way where you can remove the aliasing. And what we have here is just a video of, if you look at the top left of this image here, the pulse repetition frequency is actually changing. So at 1.4 kilohertz, you can see that every time the heart beats and emits that blood flow, that blood flow will be higher velocity because of the force of the heart. Then at lower pulse repetition frequency, you can see that rainbow our coloring red-blue artifact right here due to aliasing. But as you can see, as you increase the post-repetition frequency to 5.6, then the flow profile looks even smoother. So let's just capture that moment again here. Here. Now it's at 5.61, and there's no blue hue that you can see within this color Doppler display. Now let's talk about some examples where color Doppler is frequently used in the clinic. So an example that I showed here is the internal carotid artery stenosis. So stenosis, again, is a narrowing of the artery lumen due to some obstruction in the artery, like a plaque, for instance. So what is being done in the clinic is that this procedure is important and able to be able to gauge how much blood flow is going into the brain, because your carotid artery is actually one of the main vessels that will move blood from your heart to your brain. And if that gets blocked, then a person can experience what's called a stroke, okay, lack of blood flow to the brain. And so here what we see is that this is the carotid artery right here. And you can see that there's red and also some blue hue in this image. What this is indicating is that there could be some sort of stenosis that's causing turbulence, and that turbulence can have mixing effects at the other end of the stenosis. Therefore, what color Doppler shows is a reversal of flow as well as a forward motion of the flow. And you can also see in the spectral Doppler here that there's some negative flow components here indicating flow reversal, as well as in addition to the positive flow. So this is just one example. Another example is looking into the heart, if there are any flow defects into the heart. And the heart is a very special organ, and it's very important making sure that blood moves through the chambers of the heart in the proper directions. And there are what's called valves that are in the heart, between the chambers of the heart, to make sure that blood flows at one direction. Now, if there is a defect in any of these valves, then there could be a backflow into the other chambers of the heart, and that can cause issues with trying to oxygenate other parts of the body. So one example here is a mitral valve, one of the valves that are in your heart, and it's related to blood flow going from your left atrium to the left ventricle. Okay, and the left ventricle is the part of the heart that is useful for ejecting blood through the rest of your body. Now, if there is some backflow through this mitral valve here, then it means that not all the blood that's needed can go to the rest of your body. So here is just an example of a heart ultrasound or echocardiography. Now, we might have talked about this term earlier. So echocardiography is a common ultrasound procedure of imaging the heart. So what you're seeing here are the heart chambers. One of them is the atria, and the other is the ventricles right here. And you can see that this mitral valve, one of these heart valves, are not functioning properly because looking at the color map, you see red, blue hue that are mixing around inside the heart chambers. Okay, so this is an indication that there could be some flow reversal or backflow through the mitral valve, and that isn't not good for the heart. Another common example is in fetal ultrasound. Now, this is an image, a B-mode image overlaid with a color Doppler of a fetus at several weeks old. Now, the fetus is right here, and this is an image around the placenta right here. And you cannot delineate at this point the full picture of the baby, because the baby is very, very small at this point. But what color Doppler is useful for is looking into blood flow in that heart. Now you can see that as the heart is beating, Of course, you see motion around the placenta, but also some changes in the blood flow right here, indicating that the heart is developing properly. Okay. Now that's for color Doppler, and now I'll explain what power Doppler is. So what it is a color-coded image of blood flow based on intensity rather than direction. So if you recall, color Doppler can map the velocity as well as the direction of blood flow. For power Doppler, what it maps is the intensity of that blood flow, or the energy that's coming out from that Doppler signal. It's considered more sensitive to flow than the color Doppler, and it's also a useful tool for examining low blood flow velocity. So here's just an example of a power Doppler image. Now there's only one type of color map here, or a heat map like this, where it goes from orange to really bright orange and yellow. Yellow meaning higher intensity, so more hue, brighter hue, indicating that there is more blood flow in that region. Now here's a comparison between power and color Doppler. So on the left here, we're going to compare between Doppler signals of different frequencies and how they impact the color pixels, the image pixels in a color Doppler, as well as the image pixel in a power Doppler. So here in the left is a case where you have a higher frequency Doppler signal and a lower frequency Doppler signal. And you can see that color Doppler is mapped based on the differences in the frequencies of the Doppler signal. And that can lead to differences in the flow velocity. So you can see the intensities of the image will change. But in terms of power Doppler, now this signal has the same amplitude, let's say. In power Doppler, despite the difference in frequencies, then you don't see any change in the image pixels. Here, also because of the same amplitude, there is no change. So they're the same amplitude of the pixel. But in the case of where you have a single Doppler frequency with different amplitudes of the signal. So here we have a yellow signal, a blue signal, and a green signal, where it has the same Doppler frequency but different amplitudes. If you map the image pixels in color Doppler, this is orange or yellow, this is blue and green, you can see that their image pixels will have the same intensity. Okay? Whereas in power Doppler, because these signals have different amplitudes, so the power Doppler image pixels will, the pixel values will also vary because of the different amplitudes. It will read that the signal has different strengths here. So in power Doppler, you can be able to identify those differences in the strengths. So power Doppler is not dependent on the Doppler frequency or the velocity and the flow direction, whereas color Doppler is dependent on them. So in power Doppler, aliasing is not a confounding factor. So there's no signal aliasing because the Doppler frequency is not taken into account in power Doppler images. There's also no dependence on the Doppler angle. And what this enables is detection of small vessels with really, really slow flows. So what it looks at is it's more sensitive than color Doppler in detection of the edges of the vessels. So here's just an example of a power Doppler of a kidney right here. You can see that the color map is based on different intensities of red hue right here, where your brighter red indicates that there is more higher energy flow. Here's just another example of where the power Doppler technology has gone. So you can even look into the vasculature of a placenta, right? And you can map in 3D nowadays. Okay, so it's very useful, power Doppler, for looking at low flow velocities. But a limitation of power Doppler is that it doesn't, again, give you the velocity as well as the flow direction. So these are disadvantages, but it's widely used for looking into slow flow velocities. So I hope this gives you a good overview of color and power Doppler. We've talked about the Doppler imaging system, what the color displays are outputting. We talked about the aliasing artifact and how to eliminate aliasing by increasing the PRF. We also looked into some clinical applications of both power and color Doppler. So with this, hope you enjoyed the lecture, and we'll see you again. Thank you.